It's like every other week.
Oh, Rich, I don't know if you're knowing this, but I'm recording everything. I have like a YouTube channel. So if you ever want although some things he goes over, he doesn't really like, I mean, it's really quick, right? So, and boring. So, I don't know. This helps. If you want the link to it, I'll send it to you. Yeah. Yeah. Yeah, I can do it. Yeah.
Everyone's gonna be your friend.
Okay, any questions?
Sorry.
Please? Yes?
No.
No.
Painful to look at.
What I'll do is I'm gonna wait until after the break, probably more towards the end of the lectures, and then to the exams, because that usually gets kind of, people in different states. Tend to get distracted. We did have a communication snafu between myself and our grading assistant. He wasn't supposed to actually upload the grades yet. So I know everybody's seen their grades and they're very curious as to an explanation for their grade. We'll still hold that off until it's the latter part of tonight. Okay? So exam 2, exam 3, you'll get your exams first and then you'll see it. Okay? Other questions?
You give partial credit on the exam?
Yeah, problems got partial credits, yes. And for those, there was a couple of people emailed me saying that they're not quite done with assignment 1, and assignment 1 was also eligible for some partial credit too. If you didn't have everything done, get the points deducted for being late. I want to see the work, I want you to get through the work. The whole idea is to learn, right? And these labs are hopefully a great way for you to do that. So I want that experience out of everybody. So if you're having problems with the assignment, absolutely, we can do partial credit for that too. Okay. Other questions? Nope, you're just excited about the new material coming up, right?
Yes.
Yeah, that was it. So we're now moving into the memory subsystem, right? And we're going to take a look at how we're going to take this big chunk of memory and divide it up into shared virtual memory set spaces for our processors to manage and operate in, okay? That's where we're going to do. Here. Okay. There. Okay. So, as a reminder, processes and threads. Hey, what's that slide you doing?
Probably recap.
I don't know what that slide's doing in there. Oh, actually, it was kind of a recap, because I already started covering some of this, right? We covered the fact that processes and threads are going to simultaneously and concurrently be accessing main memory. And what we have to do is we're going to have to take main memory, divide it up, and create some management mechanisms so that we can access it from multiple processes and multiple threads within any process. Okay? They're all running concurrently, which means that our memory is not only handling the process itself, but it's also handling files. And as we've seen already, we have several different file types. So not only regular files in the sense of regular files that contain data, but also things like files that are pipes. Okay, so those also have to be handled as a file in memory as well. And as you know, pipes are going to be talking between multiple threads or multiple processes. So that means we have to manage that memory space as well. Okay, so that was kind of a reminder that when we talk about managing memory, it's not just the process, but it's also the files. So the other thing that we have to be concerned about is that the programmer will never know the actual memory location of any memory reference you're trying to make. Okay, so we spent all this time teaching you about pointers, right? Pointers are fantastic because you have the address. And now I'm about to tell you that, well, you sort of have the address. You don't have the actual true address of where that particular datum resides because you don't want to. Because you want your code, when it's compiled, to not care about what memory location it actually gets loaded into at any given runtime. You're going to launch your program. Is it always going to access at address 100? Well, that means you can only run one instance of it. So every time you log in, you create a bash shell, and you decide to create another bash shell. They can't both be running at physical address 100, because only one of them can be in memory address 100 at any given time. So that's a problem that we're going to have to deal with. Okay? The other problem that we're going to have to deal with is that because we're going to have more processes than we are memory, because that's what we're trying to do. We're virtualizing everything, right? We're going to have more processes than there are memory. We're going to be needing to swap them out, swap them back in. And when I swap them in, I don't necessarily want them to be swapped back into the same location. When your process has to go to sleep, right? Waiting for some events. It goes into sleep state, you might even get sleep swapped, right? If you're sleep swapped, that means you're getting removed from memory, you're getting to that virtual memory place that's holding the process until it gets to run state again. When it goes to run state again, I don't necessarily want it to be loaded at the same memory location it was before. What I want is a memory management and memory addressing scheme that allows my compiler to generate what it thinks is an absolute address, but isn't. And a way to translate that into a real physical address such that it can be loaded at any address and this scheme will work. Make sense? That's our goals behind this, is to come up with these virtual memory addresses that the compiler generates and a mapping algorithm to get us to a physical address. Why the books don't say that, I don't know. That's what we're trying to do. Oh, by the way, we've got some other issues to deal with. Protection. Memory protection is probably one of the most important things our operating system needs to do, right? Because after all, if I'm going to let this process load up at address 100, and this other process load up at address 100, and another one, I need to protect whatever was lying around at address 100 from this process that's being loaded into. Likewise, I need to protect addresses that are outside of my process's memory scope from that process. That way I can protect my process space from everybody else. Yes?
I think before you were talking about, is it kind of like a hash or what? Like we're going to have like kind of a virtual address and then we're going to use an
We're going
algorithm?
to look at a couple of schemes here.
Okay.
Yeah, but I want to make sure we get the concepts and the requirements in terms down first before we start looking at the algorithms. Okay? So protection. Not only do I want to protect processes from each other, I'm also going to need to protect them from things that go bad. Sometimes process will get into a bad state, or sometimes even the kernel will get in a bad state. Of course, if kernel's in a bad state, hopefully it's going to go down, reboot, and all that kind of fun stuff. But in the meantime, I still need to be able to protect all my memory from everybody else. Okay? So what that means is that we're going to do some runtime management. So compile time management, where we're going to implement this algorithm, whichever one we decide is the best one. We're going to implement this algorithm at compile time, but we're also at runtime going to have to do some checking as well. So we're going to look at some mechanisms that we can do during runtime for memory protection. Okay. Now, having said that, there are times when I want some memory to be shared amongst all processes or just a subset of processes. And so I'm gonna need to build that into my algorithm as well, because after all, if I want to share, like using shared memory segments and stuff like that, I want to provide that as a IPC mechanism, so we can have some good techniques for some good solutions for some complex problems. So let's think about how we might want to organize our memory a little bit. How many of you write your programs like this? Okay. No, this is your entire program. Well, you're right, there's stuff in there. But the point is, how many of you create the main function and put absolutely all of your work inside of main, never creating other functions or methods, never creating other objects? No one's gonna confess, right? But a lot of us, at least at one time, did that.
Trivial problems.
Yeah, okay, hello world, I get you there. Yeah. But for the most part, that's not how you write code. You write code, more like that, right? Okay. Yeah, I gotcha. Okay, so that's the way we write code, which means that our compilers are going to generate object code like this as well. So when we're thinking about how we're going to set up our memory management schemas, we might want to keep something like this in mind. This is how people write programs. And so if I want to manage my program, that means I'm managing my object code plus all the memory space it needs for the variables that you create during runtime. Okay, so that's how it's going to be organized. When I think about how I want to come up with my addressing scheme, I probably want to keep this in mind. Okay, so don't forget that. Okay, so when we talk about local organization, that's what we're referring to, is that different schemas that we're going to present are going to be optimized a little bit differently, and you might be thinking about the compiler and how it's going to have to generate addresses based upon the way we write code. Yeah.
Just as I guess kind of a pseudo curiosity point, so when we talk about like access control, or not access control, like scoping,
Mhm.
is that rooted in memory, or is that part of the compiler?
That's part of the compiler. All the scoping rules is all compiler stuff. Very important to the compiler, and it's important to us only in the sense that at this level, okay, that we need to be thinking about is that, well, we will talk about locality reference a little bit at one point for our memory management, but for the most part, all we're concerned about is organizing like this. Okay, and the rest we've all covered. So then it's all ultimately about the physical organization, right? We have the logical organization, which is from our construct of using our compiler tools to define the problem space in code, generating object code. But at the very end, that object code is machine readable executable code, and it does have to get mapped to main memory. So that algorithm for that mapping function is going to be very important to us because A, it has to be able to reach all the memory locations that we have in the machine, and depending upon whether we have a 32-bit, 64-bit, or other architecture machine, it's going to have to be dealing with those kinds of constraints regardless of how close or how far away any one function is from another. Okay, so yeah, we will be concerned about that, as well as how memory addresses, physical addresses are formed themselves. The end goal is that the programmer should never have to be concerned with whether this machine has 8 megabytes of RAM in it or 18 gigabytes of RAM in it. The programmer should never have to be concerned about that, unless of course they're a systems programmer, right? Because systems programmers are managing memory space very carefully, and they are concerned with that. But for the most part, application level programmers, and even a lot of the systems programming, you really don't care too much about that and shouldn't have to, because the operating system and the algorithms that we're talking about is going to handle that for us. It's going to chunk our executable up, our object code up. It's going to chunk it up such that parts of your code will be in memory, but not necessarily all parts of your code will be in main memory at any one given time. And of course, the more complex your system, the more true that is, your hello world program probably will be in main memory all at once. It would be very hard to fragment that one, so that's a bad example. But most of the times, you'll be, and we'll look at these, we'll see this in the algorithms, we've brought chunked up into different sizes of chunks or even numbers of chunks, whatever this chunking algorithm that we're going to take a look at is, that's what we're going to be worried about, much more so than how much memory is in the system. Let the operating system deal with it. Okay, so we talked about two of these, logical addresses and physical addresses, but there's also relative addresses. And back in your earlier classes, your architecture classes, you did direct addressing and relative addressing. That still holds true. But we're now introducing the logical address. So we can form the virtual addresses as a logical address and then come up with a mapping function to the physical address. I say that here because one of the things you talk about a lot in your 530 class is how to deal with relative and direct addresses in system space. We're not going to focus on that too much here, but we do need to be aware of it. Yes?
So where's the pointer go to? The pointer go to physical address?
So
When we talk about, point to address.
your pointer and a multi-programming operating system is going to be a virtual address, which is a logical address. That's our goal here. If you're working with a monolithic operating system, you're working with physical addresses there. But with our multi-programming operating systems, we want to work with logical addresses, so that way our operating system can translate that to physical addresses based upon what we're going to learn in this chapter. So the pointer is very much as real as when you thought it was a physical pointer. It's very much as real because the operating system's doing that translation between a virtual address and the physical address, which allows you to be able to run your same code on Rohan that you did on your Mac OS, that you did on your GNU, that you did on your Linux kernel, okay? You can run that same code everywhere because you are concerned with, when you're running your code and the pointers, with those logical addresses. Okay, so we've done our definition. Any questions on definitions and what our requirements are? Think we got it? No one's committing themselves. Okay. Well, let's see if we do. Okay. So the first technique that we're going to take a look at is called paging. Okay, so paging is all about taking our code up and memory. Let's start with memory first before we compile our code. So what paging is all about is saying, if this is what memory looks like, here's address 0, 1, 2, and so on, down to n-1. If I divide up my memory, my physical memory, this way, okay, the paging system, what I'm going to do is divide this up in equal sizes of pages. Okay, so for example, if I had I had 8 megs of memory, and I say, I want a page to be 512 kbytes. Okay? Then I can divide all of memory up, doesn't look very equal, into 16 of these, right? 1, 2, 3, 4, 5, 6, and then so on. So they're not matched up. Down to 8 megs down here, and 16 there, which would really be 0 to 15, but you've got the logical number. Okay, so what I can do with this paging technique is divide all of main memory up into these equal size 512K chunks or pages. So that way I have a page of this that I can now manage. I manage my address space with. One important thing I almost neglected to tell you is that I created these addresses. I said, this is address 0, this is address 1, address 2, and so on. But it's not the address of each and every byte. I don't want to manage by bytes because then it gets to be too small. I'm concerned about words, or maybe I'm concerned about half words because some machine instructions allow me to do half word addressing. Okay, so I might want that, but that's okay. There's a way to deal with that using masking bits, right? So I'm concerned instead with my word size. So if I'm on a 32-bit machine, because math's easier, if I'm on a 32-bit machine, how many bytes would be in one word? For 32?
4 bytes.
4. Right, so I would have byte 0, 1, 2, 3 like this, 4, 5, 6, 7 like that, and so on. So when I start talking about my memory mapping system, the thing I'm worried about first and foremost is whatever the definition of an address is in this particular machine architecture. So it's a 32-bit machine whole word addressing architecture. Then address 0 is pointing to byte 0, but address 1 is pointing to byte 4, and 8, and so on, right? So I'm already starting to make addressing a little bit easier. When I say a little bit easier, I can reach more physical addresses by saying, I'm only worried about forming the address for this byte, this byte, this byte, this byte, and so on, and I have a whole word. So word addressing, I'm going to divide memory into how many bytes it takes for one word. 64-bit machine, I would need 8 bytes, yeah? So, unless it's strictly half-word addressing machine, in which case I'm still 4 bytes. But there's different ways you can divide that up. So I'm going to define a word in my machine architecture, my word size, word length, and that's how I'll formulate these addresses. Then what I'm worried about is creating these blocks for my pages. So I decide how many bytes are going to be here's why I left that off. How many bytes are going to be in each of these chunks or each of these blocks, these pages? I need to decide how many of them. Because that will determine how many pages I need to be able to access or from a memory address. Which is important because to form addresses, I need bits, right? And so what we're going to be looking at later on is how many bits does it take to form this address? So that's why this is very important. Choosing this size is important because it's going to, well, actually we're going to come back and revisit why that's important later. Okay, so this is going to get me to the first byte of the first word in the first page. This will get me to the first byte of the first word of the second page, which is going to be 512, right? It's going to go from 0 to 511. And the next one's 512, and so on. 624, and so on. Okay? That's the idea with pages. Now, We define this on the operating system size because the compiler then knows this. When the compiler vendor is making their compiler, that's one of the things they're asking about. What is the architecture of this operating system? And you're going to say, I have 512 byte blocks for my pages. They say, fine. They program that, they configure their addressing, their virtual addressing scheme up to accommodate that, and all the math will just work. So you can compile code then such that when your executable goes to run, memory space, board space here. When your executable file gets loaded into main memory, the compiler is going to say how much memory this executable image is going to need, which is larger than the file itself, right? Because you are going to start creating your statics. You're going to start creating your first set of dynamic, and you're going to start making your stacks and function calls. So it's going to expect whatever size it's going to be. So what will happen is it will determine, the compiler is going to determine how many pages of memory are needed, because it's going to say, it's going to be generating all of the virtual addresses. So it's going to know what the length is going to be in main memory. So it's going to say, in this case, to go and load your process, means process ID 1127. When you go to load that, your program, it's to a process space, it'll tell it being the object file, the executable object file is going to tell the loader that it's going to need 3 pages of memory. And so what will happen then is when the loader says, oh, it's time to run your particular code, it's going to find 3 pages in memory somewhere. They don't need to be contiguous. We'll see that later. It's going to find 3 pages, and it's going to load your process into those 3 pages it selects. Now, we have a special name for these pages, if you will, of your process. So here they're pages, and here they are frames. Okay, so what we're going to do is we're going to create page tables, which is going to contain, and we'll take a look at that here in just a second, but it's going to contain a mapping function between your frame and the page it gets loaded in. Since your compiler already created these virtual pages inside for your process when it goes to run, it's already numbering your frames. That's going to be part of its addresses that it's pointing. Frame 0, frame 1, frame 2 in this case, if I have 3 frames, will be numbered frame 0, frame 1, frame 2, just like that. So what's going to happen is we're going to create these page tables that can then do a mapping between frame 0 and frame 4, if that's where this particular page gets selected to host this frame. Okay, so I need to provide that mapping function. That's one of the things we're going to need to do in the operating system, and we're going to do it per process. Okay, with me so far? Yes?
So you have 16 page, and for that frame you have 3 frames, so you're gonna load 3 page to that frame?
So I'm going to find 3 pages to load these 3 frames into.
To load this 3 frames? Okay.
Yes.
They're the same size, right? So-
Always, yes, they're always the same size.
So then if a process has multiple threads, the threads would still be contained within the frames that the page, that the process uses.
Right, because they're all still hosted in that single process. Yes. Important point. Other questions? Excellent. Okay, so the bottom line here, as we're going to see shortly, is that we obviously need to know the frame number, have a mapping between the frame number and the page number, and then the relative offset within that page or frame. That's going to form my address. Oh, by the way, the last frame is seldom exactly the size of a page. Right? It's got leftovers. But when you go to compile your code, it's not going to necessarily need exactly page size divided by 3 in this case, right? So at the very end, I mean, okay, take this example here, where I have 512, so I'm at 1024. My 1025th is going to go right there, right? I need a new page. So I create a new page, and I put that line of code in there. Well, if that's all the additional space you needed, you're going to have a lot of empty space here. You still need this space because you need a full page, even if it's just for one line. Well, it's seldom just one line, but it can happen statistically, right? And likewise, you might come close. You might be right at the last byte here, or just a word short of the last byte here, in which case you're being pretty efficient. But most of the time, you're somewhere in this space for your last byte that you're using in your compiled code. Okay, I just put that out there because that is one inefficiency with the paging technique here, is that you always, even if you require one additional byte or word, you need one full page.
So there's a trade-off that if you're to make the pages smaller and just give more pages to a process?
Exactly. That's the alternative, right? Well, if I'm going to have that much inefficiencies, maybe I'd make this 128 or 256, right? Yeah, you could do that. And that's what some operating systems will tune themselves to. They'll look and say, what, on average, are my inefficiencies for a number of those blocks that are in use or not, right? And they'll look at that, they might tune it, they might come back and say, let's make these 256, and you can get them more efficient that way. But the trade-off is you're spending more bytes, and we'll see this later. You're spending more bytes forming this number than the relative addressing numbers. So we're going to take a look at, we're going to come back and revisit this. But I'm glad you saw that right away. Other questions? Yes?
So if the process grows or shrinks in size, can the pages allocated to it change, or are they always fixed?
Hold that thought. We're going to come right to that. Okay, let's make sure we understand this first, because this is pictorially what we were talking about here, where in this case it's 4 pages, not or 4 frames instead of 3 in my example. But in this case here, I have initially all of my frames are available. Then I go to load process A, and A gets the first 4. Then I load process B. It only needs 3. So I go ahead and I grab the next 3. So I'm up here using the first 7, and that's okay. I come along further, load process C, it needs 4. There's 4 available, got it. Then I have this scenario here where process B now drops out. Okay, that's still okay. Process D comes along, it needs 5 pages. Well, I'm going to grab the first 3 still, and then I've got room for 2 more at the end. I'm still okay with this because my virtual address is going to have 2 parts to it. It's going to have the frame number, and it's going to have the relative offset within that frame. So every address, virtual address, has a frame number part and an address part. There's no inefficiencies for having non-consecutive frames. It's just going to go right to the right location every time. So I don't care. That's not fragmentation. I don't care. Doesn't bother me one bit. Doesn't slow me down one bit. Okay, and so this just keep going on. You'll get more and more of these separations here, and that's fine. And one, I'm going to come back to a little bit later and talk about what happens when I use this one and I need more. I'll talk about that a little bit later. Okay, so I mentioned that there is this process table, this page table, per process page table, right? And this is what it would look like. It would say, I've got this many pages, and they're loaded into these frames. Okay, so here's my mapping function, right here in the per process page table. Every process will have its own, because that way it's gonna be in memory when the process is running, so therefore the process can readily reference it, instead of having to call some other process to do the interpretation for it. Okay. So process B in that last example was kicked out, so they're all null. But process A was the first one in there that got frames 0, 1, 2, 3. So you got those and so on. So, and there you can see the mapping function, 4, 5, 6, 11, 12. I don't care if they're consecutive. I don't care if they're adjacent to each other. But you also hopefully noticed that there's one additional page table, and that's our free list. Yeah, we need our free list, right? Because if I want to request a frame, I want to go to one location. I don't want to have to search, because search takes, at a minimum, big O in, right? Usually longer. Okay, so I can, if I have a free table list, there's no searching involved. I've got the number on the first, just go to the first one. Before we talk about this, in other words, here's another cool thing that we've learned along our way of computer science. That's main memory, right? We said it looks just like this, and all of our good CE friends in here are not laughing at us saying, that's not what memory looks like. Really, we got these matrices there where you light up. Okay, don't worry about that part. This is our virtual, not virtual, but this is the way we notionally look at addresses, right? Okay. So don't go back to your CE instructor saying, you wouldn't believe what you're saying over there in the CS department. Okay, so that's main memory. We talked before about this big swap file out there in our long-term storage, right? Offline storage, hard disk, those things. Remember, we talked about this? Come on, I know we did. Okay, thank you. And we said that what's going to happen is that every process that gets created is going to be written into this swap space. Make them all look the same. They're not the same. Some geeky, some humongous, all kinds of in-betweens. Anyway, you get the idea. So they're going to get written out here into the swap space. And then the lucky ones get selected to run, which means they get put into main memory, right? So here's the deal. I have a program that when I create a process needs, I don't know, 60 frames. That's a lot of frames. Well, during the time that, during its time quantum, or during the time it runs before it has to put itself to sleep because it's waiting for an event, which of course Threads is helping us to prevent from happening more, but it still happens, right? You get the idea. Process runs and it has to go to sleep. During the course of that time, if half of those frames were never written to, or more were never written to, then I really don't need to take all of the time and resources needed to copy those frames back into swap space. Right? Because copying from memory to hard disk is a slow endeavor. It takes a lot of time. It's tying up our machine doing work that is unnecessary. If there's no changes in the contents of any of these pages, I don't want to copy it back out to swap space. Those pages that did have some modifications to it, yeah, let's go ahead and copy it out to SwapSpace because we need to. We need to get that data back out there so we can let the process swap out, another process gets to run. We agreed last chapter that was what we wanted to do, right? So it's what we want to do here, except we want to optimize. We don't want to waste time copying. Well, this will only work if we have an efficient way of determining whether or not this page has been modified, or that page, or that page, or that page. It will only work if we have an efficient way to do this, because we're doing a whole lot of these. There's a whole lot of process swapping going on, a whole lot of context switches going on. How many of you went and looked at your stats on your machines to see how many were going? High numbers, yeah? Those of you who haven't, get curious. Look at your numbers of context switches. It's really telling you a lot of information. And so what we're trying to do is we're trying to do work, because the less system work we're doing, the more application work our machine is doing. And the better our OS looks, because you're not getting the circle of death, right? How many of you have seen that circle of death? Oh, come on. How many of you know what the circle of death is? Okay, you know that little spinning wheel?
You're talking like a Mac, like the.
For the Mac one, well, Windows has one now too, except theirs is green.
Yeah.
The Mac one is rainbow colored, Windows is green, and when that circle's going, you're doing nothing, right?
This happens per process, no.
Yeah. So, to avoid the circle of death, we want to reduce the amount of work that the operating system is doing. So that way there's more work available for your application, whether it's your application that's running or you as the end user, clicking and clicking and clicking, right? So that's our goal here. That's one way to improve system performance significantly. Not do all these writes back to hard disks. Oh, no, come on. Okay. So to achieve that, one technique that we have come up with is that of using a dirty bit. Okay? It's this trade-off, right? If I'm going to dedicate a bit, a byte, a word to an operating system function, then that's a bit, a byte, or a word that's not available to our application. Well, we just talked about performance issues from a time performance, which means the processing performance is concerned. So now this is talking about memory performance in a sense, right? How much memory am I going to have to take up to do some of this management stuff? So what we're looking at is a combination of the two, and we're going to say, you know what, all I need is a single bit per page. If I have a single bit per page, I can make it like the last bit in here. And I reserve that for this thing called the dirty bit. Dirty bit, be careful here. Then what I can do is create the following algorithm. I can read, I can read, I can read, I can read. Anytime I do a write, I set the bit. I do it that way because if I do a logic test, is this a write? Has the dirty bit been set? There's two ifs already. If I just set the bit every time, less work. So anytime I do a write operation, I set the dirty bit. Okay? So the modify bit, what's called a dirty bit, we'll actually call it the modify bit. So I'll set the modify bit every time I do a write operation. Any address in that page. Then, when it's time to swap the page out into the swap space here, all I have to do is check the bit on the page that needs to be swapped. Is it set? No? Do nothing. Is it set? Yes. Copy the whole page. Is it set? No, do nothing. Is it set? No. Next. Is it the last page? Okay, we're done. Only have one page swap? Excellent.